Meet your boogers. Meet your boogers. Do a twirl. Yes, a good boy. Do a high five. That's a good high five. Do another high five. Good boy. Okay, come here. Come here. Take a bow. Take a bow. Get it. Oh, now you want something. Now you want something, huh? Do you want something, baby girl? What do you do? What do you do? What do you do? What do you do, you little toy? Oh, you get to toy. Good job. Go. Go do your thing. Go do your thing over there. I'll throw it. Good girl. Good morning. All right. Guess I will go ahead and get started. So this is SL Physics, March 29th. Okay. So so we have already talked about sort of the physics of electrons. And then we talked about the nucleus. Okay. And then, so if you notice, we went from the electron cloud to the nucleus, which is smaller than the electron cloud. And so we're kind of taking a journey inward. And so now we are going to go to what is happening inside the nucleus. So we are going to look at physics at the smallest scales that we have theories for. Okay? This is not going to be a very mathematical lecture. It's kind of more just facts. Let's start off with there are 4 so-called fundamental forces of nature. Okay. So the first fundamental force is called the strong force. Okay. Sometimes called the strong nuclear force. The second force that occurs in nature is the electromagnetic force. The third force that occurs in nature is called the weak force. And then the fourth fundamental force that occurs in nature is gravity. Okay? And so each of these forces is sort of responsible for different things. Okay? So the strong force is the force that binds the nucleus together. So as we said, the nucleus is made up out of all positive charge. Well, positive charge and then neutrons. And so, yeah, So if you just thought about the electrical repulsion of all those protons in a small space, the nucleus should blast apart because of the repulsion, but it doesn't, and that's because there's the strong force there, which is holding the nucleus together despite the repulsion. So strong force is the strongest. That's why it's called the strong force. Then there is the electromagnetic force. And this is, of course, the force that binds the electron cloud to the nucleus. Okay, because the nucleus is positively charged, the electron cloud is negatively charged. And so it's the electromagnetic force that holds the electron cloud there. There is the weak force, which has the weird property that it transforms particles. Okay. It transforms particles. So, for example, it's involved in beta decay. So, beta decay is remember, you have either beta plus or beta minus particles produced along with neutrinos. And so, in that process, protons are converting into neutrons or neutrons are converting into protons. So it changes the identity of particles, and yeah. And then you have gravity, which is, of course, the force that binds planets to the sun. Okay, and gravity is the weakest. So this is in order of strongest to weakest. Okay, so the strongest force in nature is the strong force. The second strongest is the electromagnetic. The third strongest is the weak force. And the weakest of all is gravity. Okay? So we have a theory. Physicists have a theory. Humanity has a theory of gravity by itself. It's called general relativity. Okay, so that is the theory of how gravity works. And then we also have a theory of all three of these other forces combined under one umbrella theory. Okay? And the theory that explains all three of these forces is called the Standard Model. All right? The Standard Model. And so that is what we're going to discuss today. Now, one of the major thrusts in physics right now is to make a theory, single theory, that encompasses all four fundamental forces under one umbrella theory. Because we understand how gravity works by itself. We understand how strong electromagnetic and weak forces work by themselves. But we don't have a theory that puts them together in a consistent manner, and it's proved to be really difficult to figure out how to do that because these two theories are written in such different languages. Okay? And if I can't really, basically I would just say knowing a fair amount about both of these theories that, yeah, I would say the flavor of these two theories are completely different. So it's no surprise why they're not compatible, because just the language used in each theory is completely different. So what that means is that when we have a situation where the gravitational force is playing a significant role along with these other forces, we don't know what to do, because these two theories don't play nice with each other. So if we have a situation where, if you think about like what's going on in the nucleus, both the strong electromagnetic and the weak force are all playing a significant role, okay? Especially the strong and the electromagnetic force. So the Standard Model allows us to treat that, to solve that problem, because to understand what's happening, because we have a theory that puts the strong and the electromagnetic force together, okay? But if you have something like a black hole, black holes, inside a black hole, all four forces are going to be significant, okay? And so in order to understand what is happening inside a black hole, we need to have a theory of all four fundamental forces, okay? So we call that a theory of everything. So that is a TOE, all right? Or also we'd think about a grand unified theory, a GUT. So physicists use these words. So this is one of the major pursuits of physics right now. So my goal today is to describe the Standard Model to you, okay? The first thing I want to talk about is, well, after that just introduction, is how does the Standard Model work? Well, the idea is we have particles exchange. So particles are what we would think of as matter, okay? Particles exchange force carriers. Okay? So let's suppose that here's a particle. Maybe this is an electron, okay? And here is a proton. And these protons and electrons are exchanging force carriers. So it's like they're launching missiles at each other almost. It's going back and forth. Back and forth. And those force carriers that the particles are exchanging contain the information that tells the particles how to move. Okay? So from the perspective of the Standard Model, we basically have Newton's first law. Particles go in a straight line at a constant velocity until a particle gets hit by a force carrier, and then the force carrier like gives it new information and tells it what to do. So it says, so a particle is doing its thing, going along, and then it gets hit by a force carrier, and it says, oh, I have just received this amount of momentum, etc. So I'm going to change course correspondingly, okay? So, so we're going to have, so basically what I'm going to do is I'm going to list out what are the particles and what are the force carriers, okay? And so each force in the Standard Model, so we're excluding gravity from today's discussion, each force has its own force carrier, or they might have multiple force carriers, okay? For example, the weak force has a couple different force carriers. The other thing I wanted to talk about is an additional property of matter beyond I'm going to say beyond charge and mass, okay, is called spin. Okay, spin, which is denoted by S. And basically, spin is exactly that. Elementary particles are spinning around. They're not actually spinning, but they behave as if they're spinning around. Okay, so that it's called an intrinsic angular momentum. And so you don't have to worry about what it means exactly or the physics of angular momentum, but it's basically just another property that the particle has. Okay, so particles have charge, they have mass, and they have spin. All right. Now spin is a little bit weird because spin can only take on certain values. So the spin can be 0, it can be 1/2, it can be 1, it can be 3/2, it can be 2, it can be 5/2. So basically, it can only have an integer or an integer plus a half. All right. So different particles have different spins. All right. So, and then I also want to talk about antiparticles. Okay. Antiparticles. So if you have a particle like, for example, P, its antiparticle has the same symbol, but you put a bar over the top. Okay. And so antiparticles they have the same mass and spin, but opposite electric charge. All right. So most particles have antiparticles. Most of the particles that we are familiar with. So there's an antiproton, there's an anti-electron, which I said is called a positron. There is, so there are various antiparticles. There is an anti-neutron. Of course, the opposite of 0 would be 0. So, so the anti-neutron has the same charge as a neutron. So it's almost completely identical. It's just really, really unstable. So, so I'm going to describe what are the particles. Okay. So one of the types of particles that occurs in the Standard Model is called a quark. And a quark is a particle that is inside protons and neutrons. Protons and neutrons. So, in other words, protons and neutrons are made up out of quarks. All right? And as far as I can tell, or as far as we can tell, I haven't done the experiments, there are 6 different quarks. Okay? And they have names. So there is an up quark. They have really goofy names. A down quark. A charm quark. A strange quark. A top quark. And a bottom quark. Okay? And then each of these, of course, has an antiparticle. So there's an anti-up, there's an anti-down, there's an anti-charm, there's an anti-strange, etc. Okay? So these are the quarks. And typically you draw them in a grid like this. So why do you draw them in a grid like this? Because it helps you remember their properties. Okay? So if it is in the top row here, the upper row, it has an electric charge of plus 2/3 of the fundamental charge. Okay? Plus 2/3 the charge of a proton. And then if it's in the bottom row, it has a charge of minus 1/3 of a fundamental charge. So remember how I said the fundamental charge, everything in nature has a charge that is a multiple of the fundamental charge. I lied. Quarks have a fraction of a fundamental charge. Okay? And then as you get as you move to the right here, you get more massive. Okay? Of the quarks in the universe, almost all of the quarks in the universe are up and down quarks. So almost all are up and down quarks. Why? Because E equals mc squared. So in order to produce quarks that have more mass, you need to have more energy. So most of the time in the universe, the energies involved are not enough to produce charm, strange, top and bottom quarks. So we just have up and down quarks. All right. All right. So, yeah. So almost all of them are up and down, and we need to have a specially designed particle accelerator experiment to put enough energy into the particles where that energy can be converted into the mass necessary to make charm, strange, top and bottom quarks. Okay. Quarks have spin 1/2. Okay. Now, as I said, these are the particles that are inside protons and neutrons. So what is a proton? A proton, it turns out, is an up quark and another up quark and a down quark bound together. So a proton is an up, and a down. So a proton is made up out of 3 quarks. If we looked at what is the electric charge of this, what we do is we add up the electric charge of all the quarks, and that's going to be the electric charge of the thing that they're making. So up, up, down is going to have a charge of plus 2/3 for the first up, plus 2/3 for the second up, minus 1/3 for the down. And if you add that all up, it's a charge of plus 1. Okay? So that is the correct charge. That's not really proof, but it's so you could imagine making a particle that is charm, charm, strange. And that would be an interesting particle. Excuse me. I mean, it exists. It's just really unstable. So it only exists for a brief amount of time. But it's going to be pretty much identical to a proton with the exception that it's unstable. And it is it's unstable and it's more massive. And then you could also have top, top, bottom, which would be an even more massive, even more unstable version of the proton. A neutron is up, down, down. Okay, and you can check out that the neutron has a charge of 0 because it would be plus 2/3 minus 1/3 minus 1/3 is 0. Okay, so that works out. So my point is that the charges work out. So then an antiproton, you would just take all of these and make them anti. So it would be anti-up, anti-up, anti-down. All right. So there is another class of matter particles, which are called leptons. And leptons are electron-like particles. And neutrinos. Okay. And so those are typically arranged into a row. There are 6 leptons. Okay. So let me. And again, as we go to the right along the table, we get more massive. So we have what is called the electron. Okay. And the electron has its neutrino. So there's the electron neutrino. All right. Then we have a muon. And a muon neutrino. Okay. And then we have a tau and a tau neutrino. So, so this top row, these are the electron-like particles. So the muon, the tau, this top row has a charge of -1. Okay. So all these particles are basically identical to the electron, but the muon is more massive than the electron. The tau is more massive than the muon. So muons and taus are unstable because they will give up their energy and reduce their mass and become electrons. Okay. The neutrinos have a charge of 0. Okay. So, yeah, the neutrinos are almost massless. Okay. In fact, the mass is so small that we can't even measure it, but we know that they have mass. Okay. So that was actually a big discovery when I was in like elementary school. I remember that's funny because I remember this is before I even knew what a neutrino was. I remember on the news, you know, a very serious news reporter came on, and tonight, neutrinos have mass. And that was one of the stories, and I was like, okay, cool. But we thought for a long time that they were massless, and a lot of times we approximate the mass of the neutrino as being 0 just to simplify the calculations. So, yeah, they're almost massless. The electrons are not. Leptons have a spin of 1/2 as well. Okay. And then the third class of particles are called force carriers. And as I mentioned, each force carrier has its own force that it's carrying. Okay, so for the strong force, you have what are called the gluons. So the carrier for the strong force is called a gluon. The electromagnetic force, the force carrier is called the photon. For the weak force, there are 3 force carriers. There is the W plus or minus. Oh, that's 2. The W plus and the W minus. W for weak. So the W plus, W minus bosons. And the Z boson. And so those are just telling you what the electric charge are. So Z is for 0 electric charge. W plus or minus is for Q equals plus or minus 1. The gluons have no electric charge, and the photon has no electric charge. All right? So, and then the force carrier for gravity. So remember, the standard model, which is what I'm describing to you today, is not a theory of gravity, but we kind of have already imagined that gravity could work the same way as these other 4 forces. And so we already gave the force carrier of gravity a name, even though we don't really know if it exists. And we've never measured one before. But we call the force carrier of gravity the graviton. Okay? But again, that hasn't been discovered. It hasn't been confirmed. So now let's put it all together. Oh, by the way, the force carriers have spin 1. All right. All right. So let's put it all together. So I'm going to call this the particle zoo. All right. So you have the quarks. And so I'm going to use their abbreviations now. So you have up, down, charm, strange, top, bottom. Okay. And the top row has charge plus 2/3. The bottom row has charge minus 1/3. All right. And all the quarks have spin equals 1/2. All right. Then the leptons are usually drawn below them. And so I'm going to use the abbreviated symbols for those ones as well. Okay. So there's the electron, which is an E. There's the muon, which is the Greek letter mu. And there's a tau, which is the Greek letter tau. And then the symbol for neutrino is the Greek letter nu. But then you put a subscript for which type of neutrino it is. So it's nu sub E, nu sub mu, nu sub tau. Okay. Now the top row has a charge of -1. Okay. The bottom row has a charge of 0. And then all of the leptons have spin 1/2. So the quarks and the leptons are what we think of as matter. Okay. And then we also have the force carriers. There are, and again, there are a couple of them. So there's the gluon, which is denoted by G. There is the photon, which is denoted by gamma. There is the W plus and minus. And then there is the Z. So the charge of a gluon is 0. The charge of a photon is 0. The charge of a W plus or minus is plus or minus 1. The charge of a Z boson is 0. The force carriers all have spin 1. All right. Let's talk about mass as well. So for the force carriers, the mass of a gluon is 0. The mass of a photon is 0. And the mass of the W plus or minus and the Z's are not 0. All right. So we've got matter and we've got force carriers that tell the matter what to do. And then there's another particle that was recently discovered, which is denoted H. And it sort of doesn't fit into the mold of the other stuff. And it is called the Higgs boson. All right. And the Higgs boson has an electric charge of 0. I believe it has spin 0. But now I'm questioning myself. So let's not write that down. We'll look it up afterwards. But basically the Higgs boson, through interaction with the Higgs boson, everything acquires mass. Okay? And so the mechanism by which that happens is a little bit too complicated for me to explain. It's through something called spontaneous symmetry breaking. And because the Higgs boson has spontaneous symmetry breaking, it basically acts like a drag on all the other particles. Okay? So without the Higgs boson, nothing would have mass. All right? The Higgs boson, interacting with the Higgs boson, is what gives particles mass in the first place. Okay? So it is responsible for mass. All right? So now I want to talk about the who interacts with what force. Okay? So all particles with mass, actually just all particles, even if you don't have mass, you still interact. I know that's a little bit confusing, but even if you don't have mass, you still are affected by the gravitational force. All particles move in response to gravity. Okay? It's just the weakest force. But even though it's the weakest force, all the particles react to it, which is not the case for some of the other particles, as we'll see in a second. All the particles move in response to gravity. Okay? The leptons don't do the strong force. No strong force. Okay? They do not do the strong force. But the quarks, they do the strong force. So that is why quarks are in the nucleus, because they respond to the strong force. They hear the call of the strong force, but leptons do not. Okay? All of these force carriers do the weak force. Okay? They all do the weak force. So they all do the weak force. I'm not even going to draw arrows to the force carriers, because the force carriers obviously do the force that they're talking about. And then for the electromagnetic force, only the particles with charge do the electromagnetic force. So this sort of explains why neutrons, I mentioned in a previous lesson that neutrons are passing through us constantly, but we don't notice them. So why don't we notice neutrons? It's because, or neutrinos, excuse me. Why don't we notice neutrinos? Neutrinos are coming out of the sun, they're being produced by the sun, but they don't interact with us. They're hitting us all the time. We don't notice it. Why? It's because the neutrinos have no charge. They have no electric charge, so they don't interact. So no charge. So they don't interact through the electromagnetic force. They are a lepton. so they don't do the strong force. And then furthermore, they have almost no mass. So they are weakly affected by gravity. So what they do is the weak force. Okay, they only do the weak force, neutrinos, and the weak force is one of the weakest of the four fundamental forces. So as a result, the neutrinos just, they don't have the capability to interact via the forces that the other particles are capable of interacting with. And so for that reason, they just hardly interact with anything at all once they're produced. Okay? So they just kind of are made in nuclear reactions, and then they just do their thing for the rest of eternity, basically. Another thing I want to point out is that all of the matter particles have spin 1/2, and all of the force carriers have spin 1. So there's, and then you'll also notice that there are 3 columns for both quarks and leptons. So why are there 3 different types, and they're differentiated by mass? These are called generations. So we have generation 1, 2, and 3. So why are there 3 generations? Could there be more generations of particles that we just haven't discovered yet? So there's a lot of questions about this model. So this is called the Standard Model. And by the way, we don't put antiparticles because the antiparticles are not really shown as distinct from the particles. Okay, so all these have antiparticles, but we just aren't doing. It's not really thought of as a distinct particle because it has the same properties. Okay, so the Standard Model just it it raises a lot of questions because it is so sort of random, but it describes nature incredibly well. Okay, and so physicists everywhere look at the Standard Model and they think there's got to be something deeper happening here that we're not understanding. But we can't figure out what it is experimentally. So it's like this model is just not very satisfying. It's not very satisfying to physics because it doesn't explain everything in the best way possible. I don't know. And so physicists just think that there's got to be another theory that pulls it all together. But the more experiments we do, the more it seems like the Standard Model just describes the way things are. Okay, so it's very frustrating for particle physicists. All right, so we can talk more about this if you want to in the Zoom room.